Hey everyone. I'm very great to give this talk. I hope everyone finds this interesting. So my talk is training PyTorch models on TPUs, tensor processing units. Um, so in hardware, there is no more free lunch. The end of exponential growth in computing power in the last 4 years has been reached, and software is unlikely to see significant changes, hardware-driven changes and increases on CPUs. What's that? There is a pretty common known fact, which is known as Moore's law, which states that there's a doubling in the number of transistors every 2 years. However, this seems to have broken since 2010. Moreover, the big issue comes not with the number of transistors, but with power consumption in chips. This is described by something called Dennard scaling. Dennard scaling states that as transistors get smaller, their power density stays constant, so that power stays in proportion with area. However, since around 2006, Dennard scaling has appeared to broke down. And the primary reason for the breakage is that at small sizes, there's current leakage in chips, and this makes the chip to heat up and increase energy costs to maintain the system. This means that there's an inability to increase clock frequencies, which in turn cause most CPU manufacturers to focus on multi-core processors as an alternative way to improve performance. However, having multiple cores still results in increased overall power consumption and thus worsens CPU power dissipation issues. The real limiter of chip performance is power consumption and power leakage. Since as chips get smaller, there is a higher and higher demand on power, which basically limits performance and increases cost. The solution to this problem is designing domain-specific and highly optimized hardware and software. So, for example, in domains such as big data and machine learning, software like TensorFlow, PyTorch, and JAX come to mind, and hardware such as Google TPUs, AWS Inferential chips, and Tesla's Dojo are being introduced into the space. The name of the game is basically do few tasks extremely well. So, what are TPUs or tensor processing units? They are basically matrix multipliers on steroids. So, as compared to CPUs and GPUs, TPUs have none of the sophisticated features that consume energy in general purpose chips. So, for example, there's no cache, there's no lack of branch prediction, there is no out of order execution, no multi-processing, there's no speculative prefetching, no address coalescing, no multi-threading, and there is absence of context switching. All of these make GPUs and CPUs remarkable general purpose chips, but they add significant overhead and limit performance. So as compared to CPUs and GPUs, TPUs are highly specialized hardware which is optimized for a single task of matrix multiplication. For example, a TPU matrix multiplication unit has something that is called a systolic array mechanism that can do 256 by 256 arithmetic logic units, which basically means it can process more than 65,000 multiply and add operations for 8-bit integers in every cycle. And since it runs typically at 700 megahertz, this means that there is around 92 teraops per second in the matrix unit of a TPU. This, as a result, delivers an outstanding performance to power ratio, as you can see in both the charts I present here. As you can see, TPU is 83 times better as compared to CPUs and 29 times better than GPUs when you compare the performance per watt ratio. And additionally, TPUs deliver between 15 to 30 times more throughput than CPUs and GPUs. So let's see how these different kinds of hardware work in the context of deep neural networks. So a neural network on its core is basically just a bunch of matrix multiplications between millions of floating point numbers. So how can we execute those millions of operations faster and with less power consumption? Let's see how a CPU does this job. A CPU is, as I said, a very fast and general purpose processor. It is so powerful because it can run millions of different applications just by changing software. That's why every computer and smartphone has a CPU. In the context of neural networks, it basically runs most operations in a linear fashion with little parallelism. So it's not optimized for the task of matrix multiplication. A GPU, you can think of a GPU as a bunch of CPUs with thousands of cores in a single chip. So this makes it super efficient in embarrassingly parallel tasks such as matrix multiplication, which is common in deep neural network architecture. However, both CPUs and GPUs read and write intermediate steps to memory after every calculation. This is an advantage for in the context of general purpose computing. However, it adds significant overhead in computation and increase the power consumption. TPUs, on the other hand, is designed as a specialized matrix processor with the only task of highly optimized matrix operations. It places tens or even hundreds of thousands of operators connected as a very large matrix to fulfill a single task of solving matrix operations. So TPU executes a massive parallel pipeline of matrix operations with significantly less overhead and memory footprint compared to GPUs and CPUs. For example, a single TPU version 3 chip from Google achieved 420 teraflops in processing, which is outstanding. So all of this sounds fantastic. And you might ask, why don't we use TPUs for everything? Because there is no free lunch, as I mentioned at the start of my talk. Uh, so these kinds of workflows that I'm going to describe next are not suitable for TPUs and are going to result in very, very bad performance, even worse performance than running them on a CPU. These are uh, linear algebra programs that require frequent branching or are dominated by element-wise algebra, workloads that access memory in a sparse manner, workloads that require high precision arithmetic. So in particular, there is no double precision arithmetic on TPUs. And also neural networks workloads that contain custom operators in the body of the main training loop. This means when you're running highly specialized training loops and you write your own custom operators in C++, for example, or in Python, those are not suitable for a TPU workload. So uh, so now I'm going to show you how you can use one of the most well-known frameworks for deep neural networks, which is PyTorch, and how you can combine this with XLA, which the previous speaker gave an introduction to, which is a compiler to compile PyTorch code to TPU level code, and Colab or Google Cloud, as TPUs are proprietary hardware from Google. So as the tweet mentions, once you manage to do the changes and enable training on all the 8 cores of a TPU, there's no going back. As even training with the high-end GPUs is comparatively very slow. So let's explore the changes that are needed in your PyTorch code uh, to leverage the full power of TPUs. So as I mentioned, PyTorch XLA stands for Extreme Linear Algebra. It's a compiler that connects PyTorch code and it compiles it down to TPU code. So, for example, uh, uh, there are important differences between tensors on CUDA, which you run on CPUs or GPUs, and XLA tensors. XLA tensors are lazy. They are not run eagerly. So it's important to have this in mind. The compiler basically what it does is to record operations in a graph, in a computational graph, until the results are needed. Um, and this step of deferring execution allows XLA to optimize the code. Also, there is a custom D type when running neural network workloads on TPUs, which is called bfloat 16. This is a custom 16-bit floating point format for specialized for machine learning operations. The bfloat 16 multipliers are about half the size of a typical floating point 16-bit floating point multiplier, and they are about 8 times smaller than a typical 32-bit floating point multiplier. This enables faster training and memory reduction when run on a TPU. And you can use environment variables to set XLA to use this D type in order to gain even more performance out of your hardware. So if bfloat 16 is set, the torch float and torch double D types are both bfloat 16 on a TPU. And if a PyTorch tensor has a bfloat 16 data type, it will be directly mapped and treated as a bfloat 16 D type on the TPU, and it will be compiled directly into this data type. This for people that are familiar with how you define the several pieces of your PyTorch code to run it on a GPU. There is, for example, defining the classes for your model and for your data set. There is no change you need to do for this to be runnable on a TPU. So you can basically port the exact same code um, you have previously. For the training loop, there is some minor changes. As you can see on the left is the standard PyTorch code. And on the right, there's the PyTorch XLA code. So the optimizer step, instead of being done with optimizer.step, you need to use the optimizer step from XLA model, which is used to distribute the optimization of the optimizer across all the TPU cores you have available. Additionally, if you wanna log your training loop, the printing statements in regular PyTorch are done via a print statement or using Python loggers. However, when using PyTorch XLA, you need to use the master print function from the XLA module. This is in order to only print a statement. Otherwise, you're going to print uh, as many statements as cores you have on your TPU. Remember that we are talking about distributed training. So you have each core of a TPU running a portion of your training. And if you use normal print statements or login statements, you're going to get a lot of output from each core of the TPU. Additionally, something that is recommended, uh, which you don't care at all when you're running standard Python code, it is that it is important, super important to clear the TPU memory as often as possible to ensure that your training works smoothly and you don't get garbage on the memory of the TPU. So it is important to use the delete statement to delete objects that are no longer needed, and to frequently call the garbage collector from Python to get these objects out of the memory, to flush the memory of the TPU. This is recommended so you can ensure that your training works as smooth as possible. So combining all of the previous steps, this is how the training loop would look on PyTorch XLA. As you can see, it's standard PyTorch code with the changes I just mentioned of using the optimizer step from XLA, being careful to delete objects and use the garbage collector, and printing statements for logging with the master print function. For your validation loop, there's as we discussed for the training loop, uh, the changes are very similar. As you don't evaluate gradients on the validation loop, there's no need to use optimizer step. But you still need to use master print if you need to log, and you need to still keep the memory as clean as possible for the TPU. So there is an important part which I define as the master function, which is the function that is going to be distributed across the TPU cores, and is the one that's going to run both the training and validation loops. So you need to use MP model wrapper from the XLA multiprocessing module in order to minimize host memory usage when forking the process to the different GPU cores. Basically, this means that the model weights are instantiated once in memory and not duplicated across every core of the TPU. So wrapping the model with MP model wrapper allows you to instantiate the model weights once, not once per core, which saves a lot of memory if you're training big models. So we need to create something called a distributed data sampler that reads our dataset objects and distributes batches over across the TPU cores. This is done with the distributed data sampler class from the data distributed module, and it allows to load data loaders from different cores only to load a portion of the whole data set, not all the data set. This is important, again, in order to optimize memory usage. Uh, and there is also an important step, which you need to set the number of replicas of the distributed training to the number of TPU cores you have available for your training. So typically on Google Colab, you're given access to TPU B3 chips, I believe, and those have 8 cores. So you need to set the number of replicas of your distributed training to the number of cores that you have available in order to allow the compiler, the XLA compiler, to know how to distribute the training, the model, and the data set to all the cores in order to use memory and resources as optimally as possible. And you can see that you can define in both the distributed data samplers on the right image. You need to define the rank, which is the number of TPU cores. So also, another important thing you need to take into account is that since you're running undistributed training, you need to scale your learning rate by the number of cores, of TPU cores. So since training and model has been distributed across cores, uh, and different batches are run on different cores, you need to make sure that your standard learning rate that you use uh, for your learning step needs to be scaled by the number of available cores that you have. Additionally, instead of using the device CUDA, of course, because CUDA is for GPUs, you need to use the XLA device from the XLA module in order to locate your TPU device. And you need to send your model, your wrap model, to the TPU device, which in behind the scenes, the XLA compiler is doing all the work to distribute and optimize how your code will run on the chip. Um, for You need to, as compared to regular PyTorch code, which you can see on the top image, you need to define a parallel loader from the distributed parallel loader module to load the distributed data set into the multiple cores of your TPU. So as you can see in the bottom image, you define a parallel loader object where you pass the train loader and the device. Notice that you can have an array of devices, which basically means that you can have one or multiple TPUs for this training step. And you need to replace the standard data loader in your training loop for this parallel loader per device. So per core of TPU or per TPU in a TPU pod. This is a very important and sensitive point. Typically, when you run training, you wanna maximize or minimize a metric, and once you get the minimal or maximal metric you're searching for, you wanna save your model. This is basically the end goal of training. However, uh, when in regular PyTorch code, you just need to instantiate the torch.save method, and you pass the model, the state dictionary of your model. However, this is not as straightforward with XLA tensors, because as I mentioned, XLA tensors are not eager as PyTorch tensors are. They are lazy. Uh, so you need to instead of using the torch.safe method, you need to use the .safe method from the XLA model module. This is very important because if you don't use the .safe from the XLA model module, this process will certainly fail. Uh, so the steps behind the scenes when you call the .safe method from XLA model is that tensors are moved to the CPU before saving, and if you if you directly save XLA tensors, uh, you can do it, but it's not recommended. Why it is not recommended? Because XLA tensors are always loaded back to the device they were saved from. So if you run your training on TPUs, but you want to run inference on a system that doesn't have TPUs, and you don't use the .safe method, you are going to loading the tensors or the model state dictionary or whatever you need to instantiate is going to fail, because in your current system that you are running for inference, you are not going to have a TPU available. So it's super, super important to use the safe method from XLA model. So combining uh, all these steps, uh, you can see here a snippet of the code of how the master function would look like. Again, to recap, you need to wrap your model with MP model wrapper to avoid loading the model once per core into memory. You need to define your distributed data samplers uh, with the number of cores you have available. You need to scale your learning rate accordingly to the number of cores or devices that you have. You need to instantiate your device, and you need to send your wrap model to that device. Uh, you need to also scale the total number of steps in your training loop by the number of cores or devices you have available as you are running a distributed training. You are going to run less steps, and the number of steps is going to be scaled by the number of cores or devices you have available. Also, you need to keep flushing the memory and deleting unnecessary objects with the garbage collector. And as you see on the right image, um, you still need to use the master print and everything else that we have described previously in order to for your training to run as smoothly as possible. Uh, finally, finally, um, you need to spawn the processes, which basically means forking all the previous work that you have done and distributing the training and data and model into the number of cores or available TPUs in your system. This is done by defining a map function, very similar to what Christian presented with JAX. So you define a map function which you're going to distribute across the cores you have available, and you can define certain flags that you can pass as configurations or global configurations to your training loop. This is done by defining a global variable and passing it to the map function, which in turn you can pass it to the train to the master function that we have just defined. And as you see, you need to you need to define the mprox argument, which should correspond to the number of cores you have available. So in Colab, for example, the xmp.spawn method asks the Colab instance to spin up the eight processes and use the full power of the 8 cores on the TPU chip to run whatever you have defined within your map function. And yeah, basically, once you have gone through the process of these modifications to your code, and you see how fast training works on a TPU, you're going to be blown away. Because as compared to top end GPUs like Tesla's V100s or even A100s from NVIDIA, TPUs blow them out of the water in terms of speed in training. Uh, so yeah, this is what I wanted to share with you. And if there are any questions, I'm happy to respond.